Alright, how are you guys? Let's get this party started. Okay, today we're doing series such as this one. This is an incredibly famous one, actually. It's one of my favorite ones of all times. It's my favorite one because the proof that I've seen for this one was written by the master of us all, Master Euler. If you try to write it up, you'll see that it's no enchiladas. It looks a little like this, and you try. If you're a beginner, you could be there for days and nothing will come up. Try it just for fun. Put it on pause here, and we'll see you in a couple of days. You'll see that it's not easy. But of course, if you do some digging around, you see that the answer is actually pi squared over 6. The most elegant proof by Dr. Euler. Alright, that being said, we won't always get this lucky and have the answer, the exact computed series, such as this one. Sometimes it'll just evade even, I hate to say it, but even Euler couldn't do some of these. So maybe we should take some time to review the possible outcomes that we seek. Sometimes we seek to compute the exact sum, such as this, in case you get lucky or you're amazingly powerful, you might be able to compute the exact sum. Other times you want to compare this series to something much more manageable and see how it goes. Maybe by comparing to something that's much easier, you can get some insight into that series. Other times we would just be happy just resolving the question whether or not this sum is convergent or divergent. That's just pretty much the same as what we've done before with improper integrals in the previous weeks, so it should be no surprise. However, I should point out that our course will take a little turn here, and we will focus more than ever on this piece right here. This will become our next maybe 2 or 3 weeks of the course. It will be all tailored towards this and becoming really good at trying to answer this question. When we're presented with a series like this, does it converge or diverge? That will be the question of the day for the next few days. Okay, when people say that Calc 2, the second semester calculus course, is difficult, often I think they're referring to this little bit of it. But I think if we go through it, it shouldn't be that painful. The way we're going to handle it is we're going to develop these things called tests. They're called tests because they help you test for convergence or divergence. All you do is learn the test, you apply the test, and you're done. You can see whether it converges or diverges. And so the idea is to develop a list, maybe like of 10 different divergence tests or convergence tests. And then then the idea is to become really good at using them, and then you'll be looking at these series all day long and applying one test or another and determine whether the series converges or diverges. Often the exact computation, although it's ideal, won't be that accessible. So we'll either compare to something, and ultimately by comparing we want to determine convergence or divergence and be happy at that. Clear? That's the main idea. So we start off with our first test, and I'm going to call the first test the no hope test, because consider this sum. I think it's a ridiculous sum, because if you think about it, there's no n here. All you have is a plain old 5. So if you plug in 1, you get 5. If you plug in 2, you get 5. In fact, no matter what you plug in, you get 5. And so if you were to write out the sum, it would look a little like this: 5 plus 5 plus 5 plus 5 plus 5. And if you were to add all those together, well, it would look a little like this: infinite many 5s, which of course you don't need to be Chuck Norris to figure out that of course is going to be infinity, and you're done. This is ridiculous sum because it's ridiculously easy. It's almost an insult to have it here, but it's a good place to start because we're going to lead up to the no hope test. Alright, you should know that there's nothing special about 5. We could easily exchange that for some other number, and the idea would be the same. Suppose you were adding 7s. So you'd have 7 plus 7 plus 7 plus 7. Infinite many 7s. So of course that's ridiculous. another ridiculously easy sum, it's infinity. And of course there's nothing special about 5 or 7. Watch how easily I changed those numbers to something else. Wow, voila. Those are 9s, and so it would be just as ridiculous. The point is that even if it were some crazy number like the square root of 2 plus the square root of 2 plus the square root of 2, that's infinite many square roots of 2. That's a lot of square roots of 2. Clearly this will be equal to infinity. And you're done. This diverges. That's why these sums are ridiculously easy. You might think, well, what if that number was not square root of 2 or 5 or 7 or 9? What if it was really, really small? Well, what do you think would happen if it was really, really small? Say like 0.0000151. Instantly, that's our course number, 151. In case you're keeping track. Well, that would be infinite many 0.000151s. And of course, if you do the math here, that's infinity. Capiche? What I'm trying to get to is, could we make a general statement about all these ridiculous sums and put it into one general statement that embodies the concept? The general statement says, hey, if you're adding any stuff other than 0, forget about it. Any number other than 0 times infinity will be infinity. So there's no hope of it ever converging. And that's exactly what we do. We say, hey, no matter, or negative too, if you're adding any number that's not 0, any of that, in this case, even if it's negative, it'll give you a positive infinity or negative infinity. Any number here, any number that's not 0. Remember, this is like a vampire. Whenever it bites anybody, it turns them into a vampire. Infinity times 7 was infinity, infinity times 5 was infinity. It's just too many of them. The only hope of beating the vampire would be what? A 0. Alright, so let's see. This one, now we make another change strategy here and take a look at a slightly more interesting one. Less ridiculous, but still almost ridiculous. Why? Because think about it. What would happen for n is equal to 1? Well, here, rewrite it this way. I could say 5 plus 1 over n all over 7 plus 7 over n plus 1. This is what would happen if you just do a simple rewrite with algebra. I haven't even changed the value of anything. I just divided the top and the bottom. I multiply by 1 over n, 1 over n. And when you multiply that in, you get this. And that, for large n's, this is approximately 5 over 1. Because this will go to 0. And that will go to 0. And so you're left with just a 5 and a 1. Especially for large n's. For large n's, this will go to 0. For n is equal to 1, this might be 1. For n is equal to 2, this is a half, a third, a fourth. Keeps getting smaller and smaller. Similarly here. So really, what I'm adding here is just a whole bunch of these numbers, which are approximately 5. So it's almost as ridiculous as when I was just adding 5, except I'm not adding exactly 5, I'm adding a slight variation of 5. Nevertheless, if you were to write out those sums after a while, after some long while, which I don't care how long, because this is going all the way to infinity, so I could wait as long as I need to, these will catch up. Eventually these will all be very, very, very close to 5s, and so this sum will be approximately 5 plus 5 plus 5 plus 5, which of course would be just as ridiculous as the other ones. It would be infinity times 5, which would diverge. Okay. Similarly for this one. For this one I have 7 times cosine of 3 over 1 plus 7 times cosine of 3 over 2 plus 7 times cosine of 3 over 3, etc., etc. Notice this angle is getting smaller and smaller and smaller. Eventually it will be 7 times cosine of 3 over 5,000 or something like that. So this number will be incredibly smaller. It will be going to 0. This will go towards 1. And as it goes towards 1, what's left is just a bunch of things that are really, really close to 7. This piece is going towards 1. Really, we're just adding a whole bunch of 7s. So it's almost as ridiculous as just adding a whole bunch of 7s. Here we summarize. This is just like adding a whole bunch of 7s, which of course would give you infinite many 7s, which of course would be infinity. Okay. Similarly for this one, these numbers, as you know, it's a famous limit. The limit as n goes towards infinity for n times 1 over n is equal to 1. Duh. So this behaves a lot like just adding, after a while, it'll be just adding like 1 plus a 1 plus a 1 plus a 1 infinite many times. So of course it'll be equal to 1 times infinity. And if you could do this by L'Hopital, by the way, that might be a different video if you have trouble with that. Or just have fun with it, figure out any way you want. But that limit is 1. And of course, I told you. Didn't I tell you? It's 1 plus 1 plus 1 plus 1, which of course is infinite many 1s. So this is ridiculous. You can't expect to get anything finite if you're adding 1 plus 1 plus 1 infinite many times. Right? Now we get to something more interesting. This one is not so ridiculous. And the reason it's not so ridiculous is because here's what happens. For large n's, 1 over n is roughly 0. Well, it might be a little positive number, but it's really, really close to 0, and it's a small positive number. So really, after a while, you can wait a while. The first 1,000 terms don't matter. The first million terms don't matter. It only matters what happens at the end. Because I know the first gazillion terms, if you added them all up, it would just be a plain number. It would be a constant. Whether or not this is infinite will depend on the tail, on the last infinite many numbers. So after a while, at the tail end of this, these look like a small number plus another small number plus another small number. It really looks like infinite many little numbers, which would look something like this: infinite many zeros. And this, my friends, is where the buck stops. Infinity, the vampire, could turn anybody into a vampire, but all bets are off when it starts fighting with a wolf. The wolf also likes to turn everybody into a wolf, so this is of course a famous indeterminate form. And so we can't immediately conclude that this must be finite or this must be infinite. More work has to be done to determine what's going to happen with these countering forces. This one's pointing towards 0, this one's pointing towards infinity. More work needs to be done. That's why this is a slightly more interesting sum than the other ones. And so let's summarize. That's a famous indeterminate. Let's summarize the no hope test. If your limit as an goes towards infinity, if limit is not 0, if it's not 0, if it's 7, if it's 5, if it's 1, if it's anything other than 0, then there's no hope of this thing ever converging. And you can stop right there. This is commonly called the convergence test. Okay? Again, all you do is check this limit. All you do is check the limit. If it doesn't go to 0, if it goes to anything else, or it doesn't exist, forget about it. There's no hope of convergence. If it goes to 0, all bets are off. We have a famous indeterminate form, and it gets more interesting. Alright, that's the divergence test. We'll see you here on the next time for some divergence test examples.